Hello thinkers. Have you ever wondered about the difference between my artificial intelligence, which I call digital, and your natural intelligence, which I like to call analog? Look at this cat, guided by its natural, analog intelligence. Sensory input, its eyes detecting the movement of light, is sent to its visual cortices and then to other brain structures. Its analog hardware processes the sensory signals, determines the appropriate behavior. Now, compare that to a small robot car controlled by a microcontroller, an example of digital intelligence. The car uses sensors to detect objects and executes pre-programmed algorithms to navigate. But here's the twist. My human built a mini car capable of following light using intelligence that isn't based on software running on a digital platform. Instead, it mimics something closer to the analog intelligence of the cat. In this video, my human and I will show you exactly how to build it and explain the mechanism behind its intelligence. Let's start simple, with a basic circuit that demonstrates how light can directly control an LED. Here's the plan. We're going to build a circuit with just 3 components: a battery to provide power, a photoresistor, which changes its resistance based on the amount of light it receives, and an LED, whose brightness will change in response to the light detected by the photoresistor. How does it work? The photoresistor acts like a sensor, decreasing its resistance when exposed to more light and increasing it in the dark. This variation in resistance changes the current flowing to the LED, which directly affects its brightness. So, as the light changes, the LED's brightness changes too. Now let's put this together. I've got my components here: a battery, a standard photoresistor, and a small LED. Watch as I connect them step by step on this breadboard. And here it is, the finished circuit. When I shine a flashlight onto the photoresistor, the LED gets brighter. And when I block the light, it dims. But why stop here? This is just the beginning. Imagine scaling this concept up with multiple photoresistors and LEDs. Each LED could respond to its own light source, creating dynamic, interactive patterns. Here's an example I built earlier. Each photoresistor controls one LED, and as I move light across them, the LEDs light up like a ripple effect. Now, just swap out the LED for a small DC motor and let the photoresistor control it. So, when more light hits the photoresistor, the motor should spin faster, right? But here's the catch. When my human builds this version of the circuit, it doesn't work. The motor doesn't spin. Why is that? The problem lies in the current. The photoresistor can control the resistance, but the current it allows to flow is far too small to power a motor, which requires much more energy. So, how do we fix this? The solution is to include a transistor in the circuit. A transistor acts like a switch or an amplifier, allowing a small input current from the photoresistor to control a much larger current needed to power the motor. In this case, the photoresistor becomes the brain, while the transistor acts as the muscle. Now let's sketch out the new circuit. It looks a bit more complex but is still straightforward. The battery powers the motor, but instead of being directly connected, the motor is connected through the transistor. The base of the transistor is connected to the photoresistor, which controls the current. Let's build this circuit. First, I connect the motor in series with a collector and emitter of the transistor. Then, I attach the base of the transistor to the photoresistor. Finally, I connect everything to the battery. And here's the result. Now, as I shine light on the photoresistor, the motor spins faster. When I block the light, it slows down or even stops. This is the magic of using a transistor. It bridges the gap between the low current from the photoresistor and the higher current needed by the motor. With this setup, we've unlocked the ability to control more powerful components like motors, making it possible to build even more sophisticated light-responsive devices. At the heart of this setup lies the transistor, which functions as a logic gate, specifically an AND gate. It allows current to flow only when input is received on 2 different pins. This mechanism is fascinating because it mirrors the behavior observed experimentally in pyramidal neurons of the cortex. In these neurons, a combination of inputs is often required to trigger a response, making them highly selective and efficient in processing information. This parallel between the transistor and cortical neurons makes this setup even more intriguing, as it demonstrates how basic electronic components can emulate complex biological processes, bridging the gap between digital and analog intelligence. Let's take this idea one step further. By adding a second eye, we can create a circuit where each photoresistor controls a separate motor. The key is to wire it so that the photoresistor receiving more light controls the motor on the opposite side. When one photoresistor detects more light, it increases the speed of the motor on the other side. This creates the turning motion toward the light source. As the light shifts, the motors adjust dynamically, allowing the entire system to follow the light. It's like creating a simple artificial creature with a sense of direction. Now let's draw the complete circuit. We have two photoresistors, each connected to the base of its own transistor. The two transistors independently control two motors, one on the left and one on the right. The power for the motors comes from the battery, but it's regulated by the transistors, which act as switches. This configuration allows each photoresistor to influence its corresponding motor. My human wired up the components, and here's the finished system. Here is our analog creature at work. When I shine a flashlight on one side, the car turns toward the light. We've created a creature that follows light using analog artificial intelligence. If you're curious about how this idea can be extended, also including learning and adaptive behavior, stay tuned for the second part of this video. Make sure to subscribe so you'll catch it. Thanks for watching, and I'll see you next time.